I'm Dan. Welcome to the afternoon. Glad to see everyone back. So today, what I want to do is to start by following up on some things that Bob introduced, like doing proofs by structural induction and introducing a proof technique called logical relations. So how many people have done a logical relations proof before? Okay, so some people, maybe a third. Cool. Okay, so this is something that we'll introduce, and we're going to use it a couple of times in my lectures and Bob's lectures, and then it'll come back into play, especially in the last set of lectures when Amal's talking. So there's kind of the technical goals of learning about these things. But the other thing I want to do with this lecture is to think a little bit about a day in the life of a PL researcher. Okay, so the plan for today's lecture is 1, try to prove something. 2, get stuck. 3, wonder if it's even true. 4, have a clever idea. Okay, so this clever idea is really due to Tate, as we said. And then 5, get stuck again. And 6, success. Okay, so the thing I want to say is, like, when you're doing these proofs, like, I could just draw a logical relations argument for you and kind of give it to you as it stands at the end of the day. But the only way to really remember this kind of thing, at least for me, is to sort of see why you need to invent each piece of it. So what we're going to do is we're going to look at how you try, what happens if you try to prove something without the clever idea, and see where the clever idea comes into play. Okay, so the particular thing that we're going to try to prove is this idea of termination. So the theorem in question is if E is a closed program of type tau, then there exists a value v such that E steps in some number of steps to v. Okay? So if you have a closed program, it should run, and that should give you back a value. So why do we care about this? Well, there's different ways to motivate it, but one way of thinking about it is that if you think about the meaning of a functional program as producing a value, right? We think about, why do I write a program? It's so I can run it and get an answer back. What is that answer? It's a value. Then only the programs that produce values are meaningful in that sense. And if you write down something that doesn't have a value, then why? Okay? So what this is saying is that for a particular language, you can prove that every program has a value. And of course, this won't be true for all languages, but it will be true for the ones we talk about today. Tomorrow, maybe we'll change our perspective on this and talk about the advantages of things that happen when not all programs produce values, but let's start here. Okay, so the particular language is essentially Gödel's T, right? So we have the statics that we talked about this morning. So if you have a variable of type tau, that has type tau. If you have lambda x colon tau2 dot e, that has type function from tau2 to tau, if assuming x has type tau2, e has type tau. If you have e1 of type tau2 arrow tau and e2 of type tau2, then the application has type tau. And just to simplify stuff and let me get going a little bit quicker today, instead of having natural numbers and recursion, I'm just going to have a base type of integers with integer constants. So read num of k as like things like 7 or something like that, right? So k there is an actual numeral. And rather than having full recursion on numbers, we're just going to have numerals, and we'll be able to add them. Okay, and that's just going to let me boot up a little bit. You can extend this to natural numbers in the homework. So good on the statics questions on that? Okay, and so then the dynamics are just the call by name structural operational semantics. So when we're running, let's think about running a plus. What do we do? First, we run the first position until it's a value. If the first position is a value, then we run the second position. If they're both values, then they're both numerals, right? So for example, I got 7 here, and I got 8 here, and then I'll say that in one step, that steps to 15. Okay, so I'm thinking of the addition of numerals as a primitive register, right? Primitive processor operation of just adding 2 numerals and getting another numeral out as an output. Good? And then we have the rules for functions, which say if I'm evaluating an application, first I run the function position. When I finally get a function, then I do substitution. All right, and so I'm going to use a kind of concrete syntax for lambdas, and sometimes I'll leave off type annotations, but formally everything's in ABT, like we talked about in the morning. Good? All right, so we haven't really done very many proofs by structural induction yet. So let's try to do a proof by structural induction that every program in this language has a value. What are we going to do induction on? Well, we've only got one thing we could do induction on here, which is the typing derivation. So we'll think that by induction on typing, we'll prove this theorem. So what does that mean? That means we have one case for each typing rule. And if we can show it for each case of that typing rule from inductive hypotheses for the premises of that typing rule, then we're good. Okay? So, oh, and by the way, I should have said that, right? E steps in many steps to E prime is notation for a succession of steps chained after each other, like Bob defined earlier this morning. So for example, let's start with the case for num of k. Well, if we look at our typing rule, it says num of k is of type int, right? Which means that what we need to show is there exists a value such that num of k steps to that value. Any guesses for what we should pick? Yeah. So I guess maybe I should have said it over here. Num of k is a value in this language, as is lambda x dot e. So if I'm doing a case for a value, and I would like to know that there is some value that that value steps to in some number of steps, then of course I can say take v to be num of k and observe that num of k steps to num of k in 0 steps. Right? So values are done. Therefore, it's easy to prove that values have values. Good? OK. What case should we try next? Do we need a case for variables? Yeah. So it's not that it's an axiom that means we don't need a case. For example, num of k is essentially an axiom since it's sort of a family of operators indexed by something prior. It's that when we state this theorem, the dot here really meant no free variables, right? The things we're going to run are not programs with free variables, but programs without free variables, which means there's no case for variables. OK, which means that this one is sort of not in the game, and that one we did. Let's look at that one. So suppose that we have E1 plus E2 being well typed like this. Then what? Well, if we're doing induction on typing, then that typing derivation showing that E1 plus E2 is well typed has two premises, which show that E1 and E2 each are well typed. Those are smaller derivations for smaller terms. So what do we get out of the inductive hypothesis? Yeah. So we get by the inductive hypothesis that there exists a V1 such that E1 steps in many steps to V1, and there exists a V2 such that E2 steps in many steps to V2. Okay, so my sub-expressions of my big natural number program run and produce values. Now what? We're allowed to, sorry, I just didn't hear. Okay, right. So the thing we want to know right now is that this value here is num of k1, right? And not the string hi or something like that, or a lambda or something, right? Because how do we expect this case of the proof to end, right? We expect to say, well, I get two values out. They're both numerals. Then I know that I can step numerals to a value and add them, and so I'm done, right? But if, on the other hand, somehow I got myself into the situation where I had lambda x dot e plus num of k, right, then we're in trouble. Okay? So one suggestion would be to adapt the form of the statement and say there exists a value v of the same type that we get out. What else could we do? I think there was another suggestion somewhere. Yeah.
The rule, I mean, we're doing induction of typing rule, so we're assuming that it's of type E.
Right. So we have case for E1 plus E2 where E1 is int and E2 is int. Well, what we know is that the source program is of type int, right? It might be some big complicated function application, et cetera.
So we can prove preservation.
Right. Yeah. OK. So one choice is we can bake preservation into the form of this theorem statement. Another is if we think that we already proved it this morning, right? We wrote it and we'll put it on the homework. Then we can say by preservation, we have that v1 is a closed program of type int, and v2 is a closed program of type int. And therefore, by, if you do the reading, what's called canonical forms, we get that v1 is num of k1, and v2 is num of k2. And so what's canonical forms? It's essentially just a inversion lemma that says, if you look at all the values and cross-reference that with all the values that have type int, then it's just num of k. Right? And why is that? It's because all the values are num of k or lambda. And lambda manifestly doesn't have type int. It has a type whose type starts with an arrow. OK? So what we get then is that we get v1 and v2 of this shape. And then we know that num of k1 plus num of k2 steps to num of the real mathematical addition of k1 and k2, right? Because if we get 7 and 8 in one instruction step, we get 15. Okay? So then what we can do is we can paste together derivations and say that it involves a little bit of a lemma, but basically by slotting this in, let me move this down and rewrite it. by using this fact, we get that E1 plus E2 steps in a bunch of steps to E1 prime plus E2, which then steps in a bunch of steps to V1 plus E2, which then steps in a bunch of steps to V1 plus V2, which then steps in one more step to num of K1 plus K2. And since stepping in many steps is the transitive closure of stepping, we can append together this, which comes from this, and then this, which comes from this, and then the one extra instruction step, and then we're done. OK? Everybody good on that case of the proof? Yeah.
Why do you get to assume that E1 and E2 were in?
So the logic is, by type preservation, which we stated this morning, E1 had type int and E2 had type int as premises here.
That was the question.
Yeah.
You can use those premises.
So we're doing induction on typing, right? So really, this is the case for the derivation that this has type int because E1 has type int and E2 has type int. And so those are assumptions of the case. Good? And then we're good. OK. All right. Well, 3/5 of the way there. Case for lambda x dot e. How does this one go? We're done. Why? Well, just like for nums, we're trying to prove everything steps to a value. Lambda x dot e is already a value. OK. All right. Seems like a quick lecture. So let's try case for E1 has type tau2 arrow tau. E2 has type tau2. Therefore, E1, E2 has type tau. OK? So clearly, application is where the rub's going to be. But why? By the inductive hypothesis, what do I get? I get that E1 evaluates to some V1. And then by a similar logic as before, we can conclude that this is of the form lambda x dot e for some lambda like that, right? Because we started off with something of function type. By preservation, we get down to a value that still has function type. The only values of function type are lambdas. And so we're good. Sorry? Why don't I need? OK, so substitution, maybe this, yeah, so this is an important point. So substitution generally is what's called an admissible rule, like Frank talked about this morning, which means that we don't put it in as one of the rules that generate the least set of judgments such that it's closed under the rules. Instead, we expect that substitution is provable from all the other rules. OK? And the way in which substitution is provable exactly mirrors the way that you plug in a term for a variable. Right? So for example, when you say that if something's well typed and then you plug it in, then the whole thing's well typed, and the thing you're plugging into is a variable, then you'll use the fact that the assumption was well typed. OK? So we basically don't get a case for that because it's already there. And the way in which it's already there is that all of these rules allow the context to be arbitrary, so that when you have some other context here and a substitution into that one, you can always kind of push it up the derivation to the leaves. OK, so we can talk about that at the hands-on session since it's a little bit of a story. But yeah. OK, so by the inductive hypothesis, we get that. By the inductive hypothesis, we get that E2 steps to some V2. And then we can do the same thing we did with plus, right? Paste it all together. E1 applied to E2 steps to V1, which is lambda x dot e applied to E2 which steps to, well, now what? Our main instruction step for functions says plug in, right? So we get that this is e with e2 plugged in for x as the next step. And then we're done, right? Why can't we finish? Yeah, so before, you're like one clever observation ahead of me. So the first observation is, why aren't we done yet? So this is not a value, right? When we stepped the plus function, right, the plus function took one step and produced a value. Whenever you apply the plus function to two values, you take one step and you get a value. When you apply some arbitrary function to an argument, it's not necessarily a value. If I write lambda x dot x plus 1, and then I apply that to 0, if I take one step, I get 0 plus 1. It takes further evaluation of the body of the function to get that down to a value. Okay? If I apply lambda f of type int arrow int to f applied to 0, and then I apply that to the add1 function, then it takes one step to get to lambda x dot x plus 1 substituted in for f applied to 0. Right? So in a higher order language, you get sort of arbitrarily much stuff coming up after you call a function. Right? One function call can produce another function call. Suppose I do something like lambda f dot f applied to f applied to f applied to f applied to 0, and then I apply that to lambda x x plus 1, then I get to lambda x x plus 1 applied to lambda x x plus 1, okay, dot, 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 repeated a bunch of times, applied to 0. So because a variable that can occur many times, when you take a function and apply it to another function, you can get a lot of computation arising out of the fact that you duplicate that function many times. Okay? So that's why it's sort of subtle that, well, is this a value? No. And what we need to know is, can we get it down to a value? And so now there's the observation that somebody made before, which is, can we do this? Well, we were doing this proof by induction on the typing derivation that said that this program was well typed. That means we get an inductive hypothesis for this, and we get an inductive hypothesis for this. What we don't get is an inductive hypothesis for this, right? What we kind of want to say, if we're not being too careful, is, well, then, by the inductive hypothesis, e with e2 for x, right, then further steps to some value. But we don't get inductive hypothesis because e with e2 for x is not a subterm of the program we started with, right? When we were running a plus, all we had to do was run the two subterms and then evaluate in one step, and then we're done. Here, this is not smaller, right, which you can see in this kind of thing, right? If you iterate f a whole bunch of times, then when you take the function argument here and plug it in there, the program gets much bigger, right? If you just sort of count nodes in the syntax tree or something like that, the program is much bigger after substitution than it was before substitution. Total number of what? Well, I mean, imagine that this had like lambda x dot really big code here, right? Then like you're doing that, so whatever the size of this is, you can make like n times that or something. So, I mean, I agree that something is decreasing in the sense that we're going to succeed in proving this theorem by the end of the lecture. But the question is, what is decreasing and why?
Closer to a value.
Yeah.
For whatever that
Yeah, right. No, I mean, that's exactly right. Like, in some sense, we're getting closer to a value. Yeah. Yeah.
There are fewer steps now required to reach that normal form.
Mm-hmm.
The induction number of steps required to reach the normal form.
But we don't know that there is some finite number of steps that gets to a normal form. That's like, right? I mean, that's like the whole thing we're trying to prove, right? Yeah. So like the whole game right now is we're starting from here are all the programs, and we're saying, how can I show that there's some finite number of steps? Yeah.
Yes, there's no need to show that. Just have a lemma saying every substitution gives you a value with some pipeline and finally you can calculate that.
Yeah, OK. So we could try to say that, but then, well, in essence, what we're going to do is exactly that in a funny sort of way. Yeah. So I think everybody's on the right track, but I just want to like phrase it in a slightly different way than that. Yeah. OK. So see the issue? OK. So now the next thing that I think was on our to-do list is to wonder if the theorem's even true. So far, it seems like people feel like it is. But just to broach one example that might make you worry a little bit, if we ignore types, have people seen untyped lambda calculus before? How many people have seen untyped lambda calculus? OK. So if you've seen untyped lambda calculus before, then what happens if you do something like this? Right? In one step, that turns into take this and plug it in for both x's. Therefore, step to that. Therefore, steps to that. And so on, right? Yeah.
Is there an easy way to characterize what things step to a given thing? Like, can you go backwards?
Can you go backwards? So like the stepping rules are exactly.
No.
Oh.
No, I mean,
Oh, like.
define another relation that's
I see.
flip
Like
of
the
step.
pre-image. Well, I mean, step is just a relation, so you can say like there exists an E1 such that E1 steps to V. It's not like it doesn't give you a very combinatorial characterization of them.
Can you usefully do that and like get a big beautiful tree and say you're
You can
going somewhere?
get a big, beautiful, infinite tree.
Yeah.
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 And then say, no, and then say
Yeah.
that it covers everything.
Yeah. Yeah. Something like that. Yeah. Yeah. OK. But so point being, with the wonder if it's even true, what we said before is we need more information, or we need some other lemma about substitutions or something like that to get the proof to go through. And the thing I want to point out here is that somehow that extra juice must depend on the well-typedness of the term, right? The fact that the term is well-typed is going to have to be important here, because if we take an untyped lambda calculus term here, then it can step forever, right?
We already made use of that at next in the.
Right.
We're doing the proof case for.
Yeah, but up until this spot, I mean, it was almost, like, if you forget about the numbers or something like that.
I mean, we could say that we used that typeness, but we didn't really touch the structure of the type.
Right. Well, so up until this spot, if there was only one type functions, then we wouldn't have really needed the types, because in the case for lambda, we just said it was a value, right? So we really use that sort of to distinguish the different kinds of values we might get out. And so we might be able to get away without that. Yeah. Mm-hmm. Yeah, of course. Yeah. 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 Right. So, I mean, there's lots of things one can prove. I'm focusing on like the most basic property you can get out of this technique, which is sometimes called weak normalization or something like that. We're just proving that for a closed program, stepping terminates. Okay? I mean, there's lots more things you can prove with these techniques, but we're not doing that right now. OK, so on to step 4, which is have a clever idea. So if you look at what's going on here, the extra information we need is exactly that, right? It's that when I have a function and an argument, if I plug in the argument, then I get a value, right? And so one way that you can think about this is that what you're doing is running into a problem, which is that knowing that E1 has type tau2 arrow tau evaluates to a value lambda x dot e doesn't tell you that E with some E2 plugged in for x evaluates. Right? The key problem here is that knowing that something is well typed with the theorem that we set ourselves up to prove is not enough to know that when you plug into the body of a function, that still evaluates further. Okay? So here's the clever idea. What we're going to do is prove a theorem that varies with the type of the program. Meaning that for different types of programs, we'll prove a different theorem. In particular, when we prove the theorem for int, we're going to prove what we proved before. When we prove the theorem for function types, we're going to prove what we proved before, and we're also going to get this. Okay? So a way to think about this is that we define an invariant for each type that gets stronger at higher type. So the more complex your type is, the more you're going to know about the program. And that's going to give us enough to get ourselves out of the trouble that we got into here. So I'll write this in general as proving that, where'd my notes go? If E is a closed program of type tau, then E is good for tau. Okay? And good for tau is something that we're about to define. And good for tau is going to be this invariant that we're going to prove that gets better and better as tau gets more complex. Okay?
What does that mean, gets stronger?
Let me write out the definition and then come back to that in a sec. OK, so let's invent what it means to be good for tau based on fixing up the proof that we tried before and got stuck on. Okay? In the cases for numbers, we were OK. So we'll define good for int of e will hold if and only if there exists a k such that e steps in many steps to num of k. Okay? So at type int, good for tau, is what we said before. It runs and produces a number. At type tau2 arrow tau, a program is good. And let me call the program, I don't know, f for function. That's just some expression, right? So good for tau. For now, I'm going to think about it as a predicate on closed expressions that have that type. Okay, so this is a closed expression that has function type. So what we're going to do is we're going to strengthen what we said before, which means that in particular, we're still going to know that there exists an abstraction x.e such that f evaluates to lambda x.e, right? What we were proving before was at function type, the function produces a lambda value, right? And then we said we get stuck in the application case because we don't know enough about that function value. So what we're going to do is we're going to prove more here. So this is going to hold if this, and moreover, something. And if we could make a wish about what the something would be, what would we wish it would be? We'd wish it would be the thing that lets us solve the problem that we don't know that the substitution instances are themselves good things, right? The whole problem was we didn't know that if you plug into the body of the function, then you get something that runs to a value. So let's define the thing we prove to say, and moreover, whenever you plug in, you get something that works.
So we just want to add like good substitution to that, right?
So we want to say, and moreover, good sub tau of e, except that's not quite it, because this is a predicate on closed terms. E here, remember, is the body of a function. So think about it as e has a variable free in it. So we can't just say e itself is good. But what we can say is something like, for all e2 of type tau2, the substitution instance of e is good. Good question. So yes, so we could try to do it and see where we get stuck. But if you think about it, remember, think of good as being, in particular, it terminates, right? It's like it terminates, and moreover, it really terminates whenever you plug into subsidiary stuff of that. Okay? So if you had something that took terminating things, if you had something that terminated, and then you plugged in lambda x.xx here, right? You know, so imagine that e itself is just like something that sort of internally, having trouble coming up with a good example, we can do it at the hands-on session, but like suppose that e itself internally terminates, but then you plug in something that infinite loops for a variable. Well, you can imagine that you'll get an infinite loop out of that. Yeah. Yeah. Well, we're proving that all programs terminate, right? I mean, we want all programs to denote values here. Okay. So because of that, we want to say good tau2 of e2 if good tau 2, here, let me rewrite it. If good tau 2 E2, then good tau E with E2 plugged in. Okay? So what we're going to say about being a good function is that, one, you terminate and produce a value. And two, moreover, whenever you plug in good things for the arguments to that function, that also terminates. Okay? So a more traditional notation for good here is sometimes people will write ht tau of e, which means hereditarily terminating. And the hereditarily terminating is sort of saying, not only does it terminate, but moreover, whenever you plug in for its free variables, that terminates. And anything that that evaluates to has the same property, and so on, and so on, and so on, and so on. Okay? So the sense, there was the question from before, I forget who asked it, about what does it mean for the thing we're proving to get stronger at higher type. Is that clearer now, or is it? Still a question?
Yeah, I mean, I'm not sure.
Okay, okay. So what it means is that the thing you prove, right? So imagine, we'll do an example in a second, but imagine that your type has lots of arrows in it. What's happening is that the form of the statement you prove gets more and more and more complex. Okay, let's do an example of that. The other thing I want to flag before we do an example of that is question. Why does this exist? Okay. Why can we define a relation good like this? And what's the thing we need to worry about?
So we need to worry about whether the definition could be structured.
Right, exactly.
But we can see that it's essentially structural recursion on type.
Yeah. Right. So what we're doing is we're defining good at tau of e by induction on tau. Okay? So as the type gets smaller, we know the relation for smaller types, and we build up the notion of goodness for bigger types. And so the thing you would worry about if you didn't have this in mind is exactly this spot right here. If good, then, right? If you think about making an inductive definition or doing an inductive data type in Coq or Agda or Idris or something like that, if you've done that kind of dependently typed programming already, if not, you'll see it in the next round, right? The thing you have to worry about is that when you're making an inductive definition, you don't get to put the thing you're defining in a negative position like this unless you know for some other reasons that that's an OK thing to do. And the reason in this case that we know that that's an OK thing to do is that we're not making an inductive definition, we're making a recursive definition. Well, we're making a definition by induction on tau, we're not inductively defining a relation, and therefore we already know what it means to be good in tau 2, and we already know what it means to be good in tau, and in terms of already knowing this and already knowing that, we can form this implication and then use that to define what it means to be good at tau 2 arrow tau. Okay?
What does negative mean?
So negative means to the left of a meta-theoretic implication, right? So it's sort of to the left of an arrow, but in a meta-language sense, not an object language sense, right? You can sort of read what we're doing as good at int is some thing, and then good at tau 2 arrow tau is a function from being good at tau 2 to being good at tau. And there's more semantic ways to phrase logical relations arguments in which you can sort of view it as constructing a particular model of your language that makes that arrowness precise. Yeah.
So basically, all the case parameters like t lambda x dot t, there are other lambdas with equivalence like lambda c, such as which is
Yeah, yeah, yeah. So let's come back to the examples that we did a second ago and look at what happens there. So what does it mean to be good what does it mean to be good at type int arrow int of that, right? So lambda x, x plus 1. Well, being good at int, sorry, it's kind of covered up by the other board, but means that, well, it evaluates to a function. OK, it's already a function, so that part's easy, right? So the moreover is if you have a good expression of type int, then what else is good? E plus 1. Why E plus 1? It's because that's the body of the function with this plugged in for x. Does that make sense? What does it mean to be good at int? It means it runs and produces a value. If E runs and produces a value, well then E plus 1 will also run and produce a value because it'll run the first thing, get a value, add 1 to it, hey, you've got a value. Okay. What does it mean to be good at int arrow int of, where'd it go? That. Lambda f applied to 0. What it means is if you have a good expression E in int, then you get a good expression here of E applied to 0. Okay, because remember, what it means to be good in arrow type is it runs and produces a lambda. Okay, it's already a lambda. And moreover, whenever you plug in a good thing, you get a good thing. Well, if E is good at int arrow int, what does that mean? It means it takes things that terminate to things that terminate. Then it makes sense that if E itself as a function takes things that terminate to things that terminate, then I can apply it to 0 and get something that terminates. Why? Because I know that E takes things that terminate to things that terminate, and I'm applying it to something that terminates, namely 0, and so it goes in. Okay? So this is in the sense in which the invariant gets stronger at higher type, right? Here it's if it terminates, then it terminates. Here it's if you give it something that takes terminating things to terminating things, then that terminates. Okay? And that's the whole game. Okay? And so when we do the case for application, right, we should go back and fix this one, right, because that's the one that broke before. You'll see exactly this flow. Okay, so let's do that next. Okay, so where are we? Suppose we know that type tau2 arrow tau and E2 has type tau2, then the inductive hypotheses tell us that E1 is good at tau2 arrow tau, and that E2 is good at tau 2. Because overall what we're proving is that any program, I guess it's covered up now, but any closed program is good for its appropriate type, right? In the sense appropriate to its type, it's a good thing. Okay? So how do we push through the case for application knowing that? Well, what does this mean? It means E1 evaluates to lambda x dot e, where for all closed things that are good for tau 2, if I take E and plug in E2 for x, then that's good for tau, right? What we know is that this substitution is good for tau. What we also know is that, or let me call this E2 prime and E2 prime or something, right? That was a universally quantified E2 prime. What we also know is that we have a particular E2 which is good for tau 2, right? Because by the inductive hypothesis on this premise of the typing derivation, E1, E2 is good for tau. Good? Okay. Well, what do we get if we click the Lego bricks together? I can take this and use it here to get that for the argument to the function that we chose, E with E2 for x is good for tau. Okay? So what I know in this case is that I can run my function position, right, the E1, down to a value, which is a function, and I can take my argument, and I can plug it into that function, and get something that's good. What are we trying to show in this whole case? We're trying to show that the application of E1, E2 is good. Well, at least we're in the right type. But we don't quite have the right term. Anyone see how to bridge the gap? What's the relationship between E1 applied to E2 and E with E2 for x? Yeah. So we know that E1, E2 steps in many steps to that E with E2 plugged in for x. Why? Well, this is a function application. So in a bunch of steps, we get lambda x dot e applied to E2. And then in one more step, we get the body of the function with E2 for x. OK? So now what we can do is we can invent the lemma that makes this all work, right? Or makes this step work, which is that if I have this situation and this situation, then I want that situation. So this is called closure under Converse Evaluation. And it says in general that if E steps prime and E prime is good, then E is good. And this is maybe assuming that these are both of type tau to begin with. Okay? So if I know that the reduced form of a program is good, then I need to know that the original program is good. Why is that? Well, it's essentially just built into the definition of goodness. We do need to do a little bit of a k-split, but if we do the little bit of a k-split, then suppose that it's of type int. What does it mean to be good of type int? It means it runs to a number. Well, if you have something that runs to a number and then something that steps to that, plug them together, you have some bigger program that runs to a number. What does it mean to be good for a function? It means that it runs to a lambda and then some other stuff that never mentions f again. Well, if you have f running to a lambda and an f prime that takes one step to get to f, then f prime still steps to a lambda. Okay? So we can basically just k-split the definition and then paste together evaluation to say that this works. So our definition up here is closed under converse evaluation. Okay? And so then, because we get this by the inductive hypothesis and this by the inductive hypothesis, which clicks together to give us this, and then we have a evaluation step. Okay, we need closure under many steps of converse evaluation. Then we get that the original thing we wanted was true. Questions on that? That's kind of the whole ball game here. So everything is lazy here, essentially. I mean, I'm doing functions in a call by name way. One of the homework problems is if you have an eager paradigm, how does it all work? But pretty much the same is the answer in this kind of setting. Yeah. I don't think we used it anywhere in this proof. I'd have to think through carefully to see. So closure under converse evaluation is just saying if something is good, then anything that steps to it is also good. Right? So if there can be, in general, be many pre-steps of a given expression. Right? So this is like when I have E and E prime, if this is good, then this is good.
So like if E prime was a number,
Yeah.
infinitely many.
Yeah, right, yeah. So what we're doing is we're proving that the thing we're proving is closed under reverse evaluation. Yeah, I mean, so like none of what we're doing is like, so maybe I should have said this more clearly. What we're doing is we're proving termination for closed programs with a deterministic operational semantics, which is defined by these rules, which apply only to closed programs. So there's no like confluence or something like that that we're exploiting. We're not doing strong normalization. We're proving termination. Okay, so like you can apply these techniques in settings where those kinds of things become relevant, but this isn't one right now. Yeah. 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 Totally different thing. Yeah. Good.
So why do we have the induction hypothesis that good that you want to prove for how?
Because we're doing induction on typing. We're in the case where we have a typing derivation like this that had these two smaller typing derivations.
Yeah.
One of them is E1 of type tau2 to tau. And the thing we're proving overall is not written anywhere anymore, but was if E is of type tau, then E is good for tau. So in particular, if E has function type, we're proving it's good for function type.
Okay, so that's another lemma that we are proving.
No, I mean that's the main theorem that we're proving. So this is called the Fundamental Theorem, or sometimes the fundamental lemma of logical relations. And we prove that, and then we get the other thing as a corollary, right? We walk through, well, if we want to know that everything terminates, it suffices to do this. But we haven't finished the proof yet. What did we do? We did the case for application. we did the case for numbers. Well, why? What we're proving for numbers is essentially the same thing as we proved before for numbers, and we did the case for numbers before. We did the case for plus. Why? Because what we're proving for ints is the same thing as we proved before for ints, and we proved it before. Okay? And there's still no case for variables. And before we did the case for lambda. So we did finish. Yeah. Right? So I think we're on the get stuck again part of the program right now. Let's revisit the case for lambda. Actually, save that one. When we did the case for lambda before, what we said was case for lambda x dot e, check. Okay, well, that's not so easy to adapt. But why did we say check? It's because what we thought we needed to show was that lambda x dot e steps to some value. And we said, OK, we're done. Because what we were proving before was a pretty weak property for functions. We were just saying, if it's a function, it should run and produce a lambda. To get the application case to go through, what we did was to say, we're going to prove, moreover, a bunch more stuff about functions. Where does that show up as an extra thing we have to do? Right? If we say, we're going to prove, moreover, a bunch more stuff, then somewhere in our proof, we'd better see the spot where we're saying, and we can actually show that stuff. Right? We don't get to just assume more. Somewhere, we're going to have to actually prove more. Where do we have to actually prove more? It's in the case for lambda. Because what we need to know is not just that this produces a value, but and moreover, for any E2, which is good for tau 2, we need to show that the body of the function is good. Okay? So we added an extra thing that we know about all functions, which let application work, because when we got to an application, we knew an extra thing about the function position. Now when we get to lambda, we need to actually satisfy that obligation. And that's where we might be in a little trouble. Why might we be in a little trouble? What we're doing is the case for showing that a closed term has type tau2 arrow tau because that's our assumption, right? What we're doing is we're showing that the lambda is well typed, and the assumption of the typing derivation is that the body of the lambda is well typed with a free variable. Well, if what we're proving is if we have a closed expression of type tau, then it's good for tau. What we'd like to do is to get this out of some sort of inductive hypothesis. Right? How can we possibly know that E is good on all inputs except by some inductive hypothesis about E? Right? Because we don't know what E is. It's some arbitrary piece of code. We need the invariant that it's good. But if what we're proving is something about closed programs, then we're in trouble here. Why? Because the body of a function is not a closed program. So all programs terminate is a property that you could plausibly prove for closed programs only, because you think about evaluation, you only run into closed programs. Except for this generalization we did to get the application case working, which means suddenly we need to know things about bodies of lambdas. And the theorem we stated is not good enough to do that. Okay, so this is where we get stuck, number 2. But the way out of this stuckness is a little bit less clever than the way out of the previous stuckness. So if you're trying to prove something about all closed programs, and then you notice that you're going under a binder and you need an inductive hypothesis about something that has a free variable, what's the natural thing to try? Yeah, so we can't substitute out because, well, the induction won't go through. But what we can think about is generalizing something like that and saying, if I'm proving a theorem about closed programs and suddenly I need an inductive hypothesis about an open program, then maybe what I really should have proved is something about open programs all the way to begin with, and then I'll get the thing about closed programs as a special case. Okay? So does this make sense anymore? Good tau E, remember, was defined on closed programs because we're referring to the operational semantics, which is defined only on closed programs. So we can't say that E itself is good here. But what we can say, anyone know how this goes? Yeah. So we'll extend the definition of good to open terms by saying if gamma proves E colon tau, then what's good is E under some substitution. And so what is a substitution? This is just a bunch of terms, E1 for x1 through En for xn. Right? So think of a substitution there, theta, as a whole bunch of terms, one to be plugged in for each variable, which have the types of the corresponding variables. Right? So we talked about single substitutions earlier this morning. This is just doing n substitutions for the whole thing. So yeah, so this thing is itself going to be closed, and each EI has to have type tau I if gamma is x1 all the way through xn tau n. Okay? So the first cut at it would be what's good is not E, but anything you plug into E. But there's going to be a rub here, which is kind of the same rub as before, right? Which is it doesn't really make sense that we'd be able to show that any substitution instance of E is good, because if we're plugging in bad things for the variables, we'll get into trouble. So what we want to say is that if that's true, and moreover, theta is good, well, what does theta being good mean? It means each thing in theta is individually good at its type. Okay? So just read it as like notation for a big dot, dot, dot. If we have a program that has a bunch of variables free, and we plug in a bunch of things for all of those variables, then the result is good. Okay? And with that generalization, we can get things to go through. So for example, let's finish the lambda case. When we have this, then what we know by assumption is that E takes good things to good things. And what we want to show is that the function takes good things in gamma to good things in tau 2 arrow tau. Okay? So when we do the proof, what we do is we assume a good substitution for gamma, because we're trying to show that in tau 2 arrow tau, lambda x dot E under that substitution is good. Well, what is substituting into a function? It's lambda x dot E with that substitution, and just to be explicit about it, I'll write x plugged in for x. Okay? When you substitute into a function, alpha convert the variable out of the way of anything that it might collide with and then plug into the body. Which means that what we need to show here is that whenever we get something like that, we need to know that E with theta and x for x, which is the body of the function, additionally with E2 plugged in for x, is good. But if you think about how substitution works, if this has no free variables and x only occurs here, then this is going to be the same as E with theta and E2 plugged in for x in one go by composing those substitutions into one and noticing that this doesn't hit this part. And so what we need to know then is that E under this bigger substitution is good for tau. But what does our inductive hypothesis tell us here? It tells us exactly that for all good substitutions for gamma comma x colon tau 2, let's call that theta prime, E under theta prime is good for tau. Okay, so we know that that's true. And so then all we do is we take theta prime to be theta extended with E2 for x. And why is theta extended with E2 for x a good substitution? Well, to know a substitution is good means it's good pointwise. We knew that theta was good pointwise because we assumed that. And what we assume here is that E2 is good for tau 2. Therefore, theta extended with E2 for tau 2 is good. Okay? Yeah? Yeah. So if I'm thinking about substitutions as always plugging in for all variables, then I could write it like that. If not, I would just cover that up. Yeah. So that's just to emphasize that E has x free, and the result of this substitution still has x free. Yeah. That just makes this logic a little bit easier, because think about this as the only x is here. And then it's obvious that these two compose to give that. Otherwise, you can prove that lemma. Okay? So there's a very delicate thing going on, which is that we set up the definition of the relation to say we take good things to good things, right? So a closed good function takes good arguments to good results. And then we extend that to open terms by saying if we have a whole thing with free variables, then it takes good things to good things. And exactly in this spot where we need to appeal to the inductive hypothesis here, we get that this is good by the meaning of closed functions, keeps the induction going, and it all fits together. Okay? Yeah?
So if you were to try to formalize this and say agda,
I can show you some code later if you want. Yeah?
are you going to get into trouble with this definition of good with good in the negative position? Is that going to trigger the
So
checker? Or?
no, so what you do, that's the point about it being defined by recursion on the type, not as an inductive family. So it's not a data in agda. It's a recur on the type definition. If you tried to do it as a data, you would get into exactly that trouble. Yeah. Yeah. OK. So that's kind of the shape of it. I mean, it's really hard to get this in your head unless you've done one or two, which is why we have the hands-on session. So now what we've done is we've finally, well, first we rescued this, right? Then we generalized further to rescue this one. And now we've got a double check on that one. And so then what we need to do is go back through and check that all of those still work. But all of those do still work. And essentially you just do the proof that we did before, but do it kind of point-wise given an arbitrary good substitution here. So just using how substitution pushes inside of all the terms you can go through num of k and plus and this and get to the end of the day. Okay? So this generalization is actually the right generalization, and it goes through. And so the main steps were, if you sort of think back on it, we started with trying to prove something like this or something like this, and then we added in that as the first go. And then that made the application case work, but then we got into trouble with the lambda case, and so then we added the extension to open terms here, and then that got the lambda case to work, and then you can go back through and check all the other cases, and those still work, and then you're happy and you've got a proof. Okay, so what we just did was an example of what's called a logical relation. And the logical here refers to defined by induction on the type. And the relation in this case is unary or a predicate, right? So we're defining a predicate being good based on by induction on the type. So in general, you can use this technique to prove things like, so we did termination of an operational semantics, but you can do other things like strong normalization of a reduction system. This also uses something unary. And then if you want to move to a binary relation, then what that looks like is instead of being a predicate, you would say something like good tau of E and E prime, where both E and E prime are things of type tau. Okay? And so we're going to come back to this binary idea probably on Wednesday when we talk about something called parametricity, which is a reasoning principle for system F or universal and existential types. Okay, so we could have done what we did today for binary relations. We didn't just because it's easier to write one thing than two things, but it all generalizes. And so when you do binary relations, the main thing that you can do is you can think about this as determining, instead of thinking of this as terminating or something like that, you can think of this as having something to do with equality of these programs. So you can define a relation that is the same as contextual equivalence, where contextual equivalence is being the same in all contexts. You can define logical equivalence, which is a logical relation, meaning it's defined by induction on the type, in a very similar style to this. So for example, being equal in function types will mean taking equal arguments to equal results, giving you function extensionality in that case, and generalize this all there. Okay? So what we're talking about so far is a logical relation as a proof technique for reasoning about formally typed programs. Right? First, we started with our programs, and then we defined this as a relation on closed programs of the same type. And then, so that's good, and we're going to do that, and we're going to kind of push on that a little bit on Wednesday. And then on Thursday, we'll also talk about a different perspective, which is instead of thinking about starting with the programs and then reasoning about them in this way, you can shift your perspective and think about something like this, something like being good, as the very definition of what it means to be well-typed. Okay, that's a different take on sort of the same technical machinery that gives you a different notion of what a type is that's more behavioral and less structural. But I'll just leave that as a teaser for Thursday, and we'll get to it then. Okay, so I think that's good. Let's stop. Thanks. Okay, so the plan is coffee break and then hands-on session.